Okay. Let's start, my dear students. Question 1. A star has a luminosity that is known to be 4.8 into 10 power 29 watt. So this symbol is L. You have the luminosity. A scientist is observing this star. If he finds that the radiant flux intensity of the star received on Earth is this 2.6 nanowatts per meter square, F, radiant flux intensity. Name the term used to describe an astronomical object with known luminosity, standard candle. This is a beautiful definition of standard candle. Astronomical object with the known intensity, known luminosity is called standard candle. After that, determine the distance of the star from the Earth. Which equation helps you in this? So we know F is equals to L over 4 pi d square. Rearrange, so it will be d will be L over F times 4 pi square root. Substitute the values. L is luminosity 4.8 10 power 29. 4 pi F 2.6 nano. Nano means 10 power negative 9 square root. Three point eight three 10 power 18 meters. So we organize the information. We have total 6 equations in this topic. So certainly you will not struggle for this. After that, let's read the next question. Sun has a surface temperature this. Wavelength lambda max of light to which the maximum rate of emission is this nano. Okay, so Wien's displacement law, right? So if you have this temperature, so lambda 1 max will be 500 nano. Scientists observing finds that the wavelength for which the maximum rate of emission occurs from the star is this. So maximum wavelength mean lambda 2 max is this. Show that the surface temperature of this star is this. Show that mean you want to find T2. Explain reasoning. So explain reasoning means sentence. What sentence? Wien's displacement law. So that's the reasoning. So first they using Wien's displacement law, it says what? The lambda max inversely proportional to what? Surface temperature, right? Okay, now you can write, or you can write like this, lambda max times T is equals to constant. This is the explanation. Now substitute the values. Lambda max 1, 500 nano. T1, 5800 Kelvin. Lambda max 2, 430 nano. T2, we don't know. You can simplify 10 power negative 9 and now rearrange 500, 5800, 430, T2. First write the actual answer, then write the 6,700 Kelvin. It's fine. 6,744, which rounds to this. So whenever they ask you to explain, please don't forget to write the reason. Use the information to determine the radius of star. Now look, radius of star, we have only one equation, which is Stefan and Boltzmann's law. Stefan and Boltzmann's law tells that it says that the luminosity of a star is 4 pi r square sigma T4. Do you have temperature of this star? Yes, 6,700. Sigma you will take from the sheet. R you want, luminosity you have. Yes? So R will be L over 4 pi sigma T4 square root. Luminosity of the star was luminosity 4.8 10 power 29. 5.67. What did I tell you? 10 power negative 8? Temperature 6,700 power 4 square root. Since they ask you to show that, so I'm using the same value of the temperature. Ten power 10 meters. What is meant by luminosity of a star, my dear students? Luminosity of a star, you know, it is the total radiant power emitted by a star. Total radiant power emitted by a star is called radiant luminosity, while radiant flux intensity is per unit area observed on Earth. Dear students, organize the data. Luminosity of a star is this, underline letter L. Distance between Sun and Earth is this, letter D. Radiant flux intensity F, easy. Give a unit also. Unit is watt per meter square. One point five one 10 power 11, sorry, 4 pi so 1,340 watts per meter square. Watts per meter square. Use the data to calculate the mass that is converted into energy. You already know. You already know Mass energy equation is only one, Einstein's equation. E is equals to mc squared. So first you need energy. It's every second. What? So every second mean time is 1 second. Energy is power multiplied by T. So which is power is the radiant power, which is 3.83 10 power 26 into 1, which is 3.83 into 10 power 26 joules. You need mass. So mass will be energy over C square. C, this much mass changes into energy. Kilograms. 4.26 10 per 9 kilograms. The radius of sun is this. Radius of any star is only related with one equation, which is Stephan and Boltzmann's law. The surface temperature is T you want to find. Yes? So Stephan and Boltzmann law says luminosity of sun is 4 pi r square sigma T4. So T will be L over 4 pi r square sigma fourth root substitute L 3.38 10 3.83 10 power 26. 4 pi r 6.96 10 power 8 sigma 5.67 10 power negative 8. It should round to 5770 Kelvin. So again, here you use the radiant flux intensity equation and Stephan and Boltzmann's law. I didn't use radius square, but my answer is still same. Okay. The wavelength lambda max of light for maximum rate of emission is this. And surface temperature is this. Use the information to determine the wavelength of light from this another star. Okay. So this star is, you can say temperature 2, and you can say the wavelength lambda 2 max. Okay. Star is serious? Okay. All right. So the first for sun, it was lambda 1 max. Wien's displacement law says what? They didn't say to explain, so directly write lambda 1 max times T1. Lambda 2 max times T2. Lambda 1 is 5 into 10 power minus 7. Temperature was 5770. Lambda 2 is unknown. T2 is 9954. Three significant, please. 10 power. State Wien's displacement law. The wavelength at maximum intensity is inversely proportional to surface temperature of star. Wavelength at maximum wavelength of maximum intensity is inversely proportional to thermodynamic surface temperature of star. I just added thermodynamic just to make sure it is in Kelvin scale. Otherwise, it's fine. Figure 10.1 shows the wavelength distributions of electromagnetic radiation emitted by two stars A and B. The surface temperature of star A is 5800. Determine surface temperature of B. Before you find, you need to know their wavelength at peaks. Star A is 0.5 exact. B 0.6765. Lambda A, lambda B. Both are max. Khalas, Wien's displacement, they are micro, but doesn't matter. So lambda A max times TA, lambda B max times TB. For A, it is 0.5 micro. Temperature is 5800. B is 0.65 micro. Temperature of B, we don't know. Micro, you can simplify, which is 4500 Kelvin. So you understood how do we read the graph even? So the wavelength we see, when there is maximum intensity, you read the x-axis, it gives you the wavelength. Given data in the question is if it's 3, you can write 3. If it is 2, you can write 2. 4460 is correct, you can write it. My given value was already 2 nearest to 100. So I wrote in the same way. Star B appears less bright than star A when viewed from Earth. This, okay, we know less bright mean what? It might be far away, yes or no? Or it might be a smaller star. Yeah, less surface luminosity. Use the figure 10.1 to suggest with the reason how else the physical appearance of star B can be, other than intensity. Huh. Star B, wavelength. Wavelength, peak wavelength detected is what? Longer wavelength. Doppler shift says what? If the observed wavelength is longer, what does that mean? It is further away. So further away is appearance, my dear, appearance. What do we call this? Observed wavelength is more. What do we call this?
More redshifted?
Redshifted. So it is more redshifted, so this appears redder, more red. Red, redder, reddest. So it appears redder, my dear, yes or no? So it has a greater wavelength at peak intensity since this is a reason. Since star A has greater wavelength. Light is the same. Every light is same, but greater wavelength at peak intensity. So, sorry, I didn't listen. Star B appears more red than A. Yes, Taha, you are right, my dear. So, Doppler shift, more the change in wavelength, more the red shift, more red shift. So appears red. Appearance, they ask you. So, what is the meaning of red shift? I already told you. The observed wavelength is greater due to recession of a star from Earth. Observed wavelength of light from star is greater, yes, due to recession of star. Recession means moving away from Earth. How the cosmologists are able to determine that the red light from distant graph has undergone redshift? Okay, so observing, by observing which spectral lines, my dear, of light from distant star and comparing with the spectral lines of light from Earth. From distant star and comparing with spectral lines of light from Earth, from source on Earth. Hubble's law, my dear, you already know. What is Hubble's law? Speed of recession of a galaxy is directly proportional to its distance from Earth. How the cosmologists use the observation of emission spectra from star in the distant galaxies to determine that universe is expanding. Yes. So observed wavelengths are longer. Yes. So which gives a redshift, which proves that the stars are moving away from Earth. Observed wavelength of spectral lines from stars in, I'm using the same words which are in question actually, okay? Stars in distant galaxies is greater, showing a redshift. So stars are moving away from Earth. So if they are moving away, I mean universe is expanding. I think if you do this question after that, you will not be having anything left. All the 6 laws, equations are applied? No. The Doppler shift we didn't apply yet. The delta lambda over lambda. How Hubble's law and the idea of expanding of universe leads to Big Bang. Okay, Hubble's law says that the speed is increasing as they are moving away. Yes? And Doppler's effect says the universe is expanding. If this is true, so back in time, all these galaxies, they started from a single dense and very hot matter. Yes? Then an explosion took place and they started to move away. Yes or no? So, right, according to directly say as all parts, they say universe, right? Universe are moving away from. Can we also write they're expanding? We already wrote expanding. So I'm going after this. Oh. Can you see that? Yeah. So now I'm saying away from each other. I gave you the example of so put some dots on a balloon and inflate the balloon. So every dot is going away from each other. All parts of the universe, they are moving away from each other. So now incorporate Hubble's law. So Hubble's law says more distant objects. This is Hubble's law. Move away faster. If this is true, then they all must have been very close in past and started to move away from what? Single, dense, and hot matter due to an explosion. Space is not enough, but concept is enough. Copy. This whole question is theory. None of the equation we use this. None of the equation. What is meant by luminosity of a star? Total radiant power emitted by a star. Total radiant power emitted by a star. Everything came in 22. Yeah. Total radiant power emitted by a star. A star in constellation Canis Major is a distance this from Earth. Distance D. Luminosity L. The surface temperature T. Calculate the radiant flux intensity. F is equals to L over 4 pi D square. 8.14, 10 power 16. Now see all the data values are 3 significant. Now we'll keep three significant. You will keep three significant figures. Luminosity is 9.86 10 power 27. 4 pi 8.14 10 power 16 square. Minus 7 watt per meter square. Radius of star is only related with one law, and that law is, you say, which formula has radius of star? Stephen and his friend's law. Stephen and his friend's law. Radius of a star, Stephen and Boltzmann law says luminosity is 4 pi r square sigma T4. Rearrange, radius will be L over 4 pi sigma T4 square root. L 9.86 10 power 27 sigma T 9830 power 4. 1.9 1.22 10 power 9. Explain how surface temperature of a distant star may be determined from the wavelength of spectrum of light from a star. Actually, we did a while ago. This is the method. This is the method. How did we find surface temperature of this star? Number one, we plotted their intensity and wavelength graphs of the spectrum. Yes. Then one with the star with known temperature and one with the star with unknown temperature. Yes. And then apply Wien's displacement law. Again, how can you determine the surface temperature of a star? Again, your first step is using their spectrum. We plot there the intensity, and it's wrong. The y-axis, there are rate of emission. We say intensity and wavelength graphs. We determine the wavelength at their peak intensity of the spectrum and of the star with known temperature and the star with unknown temperature. And then we apply Wien's displacement law. So you have two stars, my dear. Yes? So you determine wavelength of peak intensity of star of unknown temperature and wavelength of peak intensity of star with known temperature. Then apply what? Wien's displacement law. Yes, that's it. 1 mark for known, 1 mark for unknown, 1 mark for Wien's law. That's it. We don't have numbers, so you can just write the way you want. But no way. What is this? Looks like quantum physics. Anything with non-quantum we can solve. By mistake, maybe I added this. How the emission spectrum evidence existence. No, this is quantum physics. Quantum. Yeah, maybe part B only. Part B, because previous is the quantum physics. Okay, the same part of emission spectrum of iron in part A is observed in the light from the stars in a distant galaxy. The numbers indicate the wavelength in nanometers. Go back. The wavelength was 411, 435, 488, 658. Now all the wavelengths are more or less? More. So more wavelengths mean what? Redshift. Increased wavelength, moving away. Say the name of the phenomena that gives rise to change in wavelengths. It is increased wavelength, so it is a redshift, my dear. If it is decreased wavelength, you will say blue shift. But this is what? A redshift, my dear. State what this phenomena shows about the motion of galaxy. Of course, moving away from Earth. Did they use the word Earth or observer? One of the lines and the corresponding lines use them to find the speed. Yeah, this is the only equation which we didn't use so far. To find the speed of the galaxy. Speed of galaxy, you know, delta lambda over lambda is V over C. Use one of them. Can we use the first one? 411 nano and observed is 429 nano. 429 minus 411 over 411 nano V over C. They say use any of them. So difference in wavelength is up, down is the actual wavelength. You can use any, but corresponding ones. Multiply and solve. So 1.31, 10 power 7. The galaxy is known to be at this distance from Earth. Use the value to find Hubble's constant. I already know. Hubble's law is V is equals to H naught D. So H naught is, I thought I need to memorize. Control. Okay, V, 1.31 into 10 power 7. 5.7 into 10 power 24. 10 power negative 8. Question number 7, my dear students. A student observes different stars from Earth. Give 2 reasons why some stars appear brighter than others. We already studied the brightness or their luminosity. I mean, radiant flux intensity on Earth. It depends upon what feature. So they could be, one is the distance, like there's less distance from the Earth, and other is their own luminosity. So brighter stars are closer to Earth, means less distance. And the second reason was luminosity, greater luminosity. So brighter stars have greater luminosity. Next question is, what is meant by standard candle? Standard candles, you know, astronomical objects with known luminosity. A spectral line from a star within the galaxy is observed to have a wavelength of 690 nanometer. The same spectral line is measured in the laboratory, is observed to have this one. So, my dear students, certainly the Doppler's redshift, that was the sixth equation. So, lambda, lambda, certainly the longer wavelength is from the distant star. Yes, shorter wavelength is from the Earth. Okay, show that the speed of the star relative to Earth is this. This is called speed of recession you want to find. So rule was delta lambda over lambda is equals to V over C. Delta lambda is the change in wavelength, my dear students, which is the longer, which is 660.9 minus 660.9 minus 656.3 nano over which one? The smaller one, which is on the Earth, 656.3 nano. V over C, V over C. C is 3.0 into 10 power 8. You will rearrange and your answer will be 2.1 into 10 power 6 meters per second. Actually, this was the sixth formula. It is about Doppler's shift. Change in wavelength over wavelength, V over C. V is the speed of recession and C is speed of light in free space or vacuum. Calculate the distance to the star. Hubble's constant is this. Hubble's law says V is proportional to their distance. So V is equals to H naught D. So D is V over H naught. So V is 2.1 10 power 6. Hubble's constant 2.3 10 power negative 18. You can calculate and give me the answer to two significant figures. 9.13 10 power 23. All right. Now they are asking you, state and explain what can be concluded about universe based upon this change. Okay, this change means what? Observed wavelength is longer. Observed wavelength longer mean the light is redshifted, means what? The distant galaxy or the star is moving away from the Earth. When it is moving away from the Earth, it means universe is expanding. So write all 3 points, my dear students. So based upon that wavelength, since observed wavelength of light from galaxy, they use the word, is this light was from where, my dear? Yes, is greater. Increased, yani, yes? This means what? The galaxy is moving away from Earth. Moving away from Earth means universe is expanding. Very to the point answer. Observed wavelength, more. Yes? Which means moving away. Moving away means universe is expanding. You can mention the word redshift and it doesn't make a problem. After that, question number 8. Question number 9, my dear students. State Hubble's law, identify any symbols you used. Hubble's law, my dear, the speed of V is the proportional to the speed of recession of a galaxy from Earth is very good, proportional to its distance from Earth. I didn't use a symbol. If you use a symbol, then you will say V is equals to H naught D. Then you need to say what is V, what is D, and what is H naught. This blue is another answer. Yani, V you will say speed of recession. D you say distance from Earth. H you say Hubble's constant. My dear, red response or blue response, both responses are correct. It's your choice. If you write the equation, you need to define this. A star of luminosity, luminosity symbol is letter L. A distance from Earth, lowercase d. Calculate the radiant flux intensity, very easy. F is equals to L over 4 pi. Students, please calculate it. So L over 4 pi d square. Make the calculations. 9 point 10 power negative 19. 9.3 into 10 power negative 19. Copy, my dear students, please. The star in B is in a distant galaxy. A spectral line in the light from this galaxy is known to have a wavelength of 486 nano. The spectral line in the light from the galaxy observed on Earth is this. Now, this is observed and actually is supposed to be 486. Why the wavelength observed on Earth is different from known to be emitted? Of course, my dear, redshift. What is the reason of redshift? Moving away. So write this. Galaxy is moving away from Earth. When you know any object is moving away, when a source is moving away from the observer, what happens? The wavelength of light is, actually we say observed wavelength of light is increased. You can say according to Doppler's effect, yes or no? That's it, 2 marks due to redshift. Determine the value of Hubble's constant. Okay, so now my dear, indirect question. Hubble's constant, you know V is equals to H naught D. So H naught is, I can tell, 2.3 in 10 power negative 18. Okay, so it is V over D. So it means V we need to find first. Using Doppler shift, you know delta lambda over lambda is equals to V over C. Delta lambda change in wavelength 492 minus 486 nano over 486 nano V over C. V is 3.7 into 10 power 6. Okay, this is your step 1 to first find what? The speed. Substitute here. So H naught will be 3.7 10 power 6 over D 1.8 10 power 24. It is supposed to be the same number, right? Is it?
2.1.
What came? 2 point? Did you round the previous answer? It's 2.0 57 10 power. Let's write 2.1 then. Okay, you have to write according to the calculations. Make sense, my dear students? Copy this. Mass defect. Mixed question, okay. So mass defect, my dear students, you already know the difference in mass of nucleus and the mass of individual nucleons. Yes or no? Difference in total mass of individual nucleons and mass of nucleus. This difference is called mass difference. Fine. Okay. Individual, separate, any word could be used. Figure shows the mass defects of three nuclei, hydrogen 1, hydrogen 2, and helium. So fusion reaction takes place, hydrogen 2 and hydrogen 3, they give you helium and X. Balance, my dear. 2 plus 3, 5, so this is 1. 1 plus 1, 2, so this is 0. Which particle is 1, 0? A neutron. It's a neutron, my dear. Show that the energy, and take this we will be solving in a while. How show that the energy released with one nucleus of helium is formed in this fusion reaction is 2.8 into 10 power negative 12 joule. So you need to first find mass defect. 0 point. Helium is 0.03037 and hydrogen was 0.0. Still, it's the same thing. Change in mass of each. 0, 2, 388, 0.00, 9105. Give me this mass defect first. Do not round, my dear students.
0.01
0.0
3x
and
4
4 bus
3x
U is equals to mc square. We have the mass defects of E. There is no mass defect for the neutron, okay? So give me the answer. 0.018884 1.66 into 10 power negative 27, 3 into 10 power 8, square. Calculate. 2.8, 10 power negative 12. You can round to 2.8, 10 power negative 12. Actually, they did not give us the masses. They say mass defects. So mass defect over there, mass defect over there. So overall mass defect, you can say. One is excess, other is defect. So overall, they gave you the values. There is no mass defect for the neutron. Nothing real. I only use the total mass defects during the reaction. The star has a radius luminosity L. All the energy released from the helium is radiated away from the star. All the energy is radiated from the star has been released in the formation of helium. That is radiated from the star has been released from helium. Okay. The mass of helium produced per unit time by the fusion. So how much mass is produced? The energy, sorry, the total luminosity you have and the distance you have. How this distance and luminosity will help you using this energy to find the total mass of helium produced. Listen, first of all, this energy is only for one helium. Yes, this is for one helium. Mean this energy is due to mass of one helium. Yes, so you can use this equation to find the total energy, right? Yes, and after that, you can convert that into mass using the mass of one nucleus and how many you can find, my dear students. So there are different ways. You already have this total. This is the radiant power. Do you have time? It's already written per unit time. Per unit time. So actually that energy is this many can I say joules per unit time? Can I say or no? What is power, my dear students? It is joules per unit time. So now using this and previous energy, I can find the number of nucleons. How many helium nuclei are there? So I will find the total number of helium nuclei per unit time. Dear students, total energy is 1.4 into 10 power 28 joules per unit time. Divided by one nucleus, how much? 2.8 into 10 power negative 12. This many nuclei will be per unit time. Per unit time, yani per second. 39 nuclei per unit time. This many nuclei. Now, mass of one nucleus is how much? 4u. So the total mass will be how much? 4u multiplied by number of nuclei. 4 into 1.66 into 10 power minus 27 into 5.0 into 10 power 39. Calculate, my dear.
3.22
3.10 power 13 kilogram. So this is the total mass which you expect to be changed into helium due to this energy. Again, my dear students, the watt luminosity is actually energy per unit time. So using the energy of one nuclei, I found total number of nuclei. Each nucleus mass is 4u, I found the total mass. Surface temperature. Which equation relates the luminosity with surface temperature? No idea? It starts with the letter S. Stephen and his friend's law. Very good. Using Stephen and his friend's law, it says L is equals to 4 by sigma d square T4. So T will be L over 4 pi r square sigma fourth root. Put the values, my dear students. Stephen and Boltzmann's law. Luminosity is 1.4 into 10 power 28. Radius 2.3 10 power 9. Sigma, 5.7 into 10 power how much? -8. Take the fourth root, my dear students.
7.
7, 7,800 kelvins.
Where did we get 5.7?
Sigma, it's 5.7 or 5.67? Sigma, value of sigma. I'll highlight for you. Okay. It's the same question actually. It's the same question. Yeah. State Wien's displacement law. What does it say, my dear? Is directly proportional to surface temperature of star in thermodynamics in absolute scale. So wavelength, maximum intensity is inversely proportional to what? Surface temperature of a star in Kelvin. Alas, this is more easier. Okay. A cosmology student observes the electromagnetic radiation received from a star in a galaxy. The student uses Wien's displacement law to estimate the surface temperature of star, a standard candle to estimate the distance, a Stephen Boltzmann law to estimate the radius. We wrote this sequence in the question also, how different things are found. So state what is meant by standard candle. Stay, my dear students. An astronomical object with known luminosity. State the reason why the radiation from the star are redshifted, it's moving away from us. You can say star or you can say galaxy is moving away from Earth. If you just want to append the sentence, so the observed wavelength is more, it's accepted. But you must say because it is moving away from the Earth, so it is redshifted, more wavelength. The true values of the quantities observed or estimated are those that are recorded to allow for redshift. However, the student does not correct them for redshift. By placing one tick in each row, complete the table 10.1 to indicate how observations and estimates made by the student compare with the true values, maybe. So first of all, wavelength. You already know compared to the true value, the observed wavelength is more. Last column. Yes or no? We already know red shifted. Red shifted. Surface temperature, you already know. Wien's displacement law says what? The peak wavelength, surface temperature, inverse. So surface temperature of students' uncorrected data, what do you think? Say, my dear students, if you keep further on the wavelength graph, this is wavelength on x-axis, yes? So instead of observing this wavelength, imagine you observed this wavelength. So temperature, more or less? Inversely, you already wrote at the big top of the question. So, why more?
The temperature will be high.
You are mixing up, my dear. That's intensity. Means displacement loss if your wavelength is here. If your wavelength is longer. Yes? Peak, okay, let's make it a bit more neat and clean so that you can understand. Please pay attention, my dear. This is correct. Okay? So the peak wavelength was here. Yes? Now, but you did not detect this one. You detected this wavelength. Detected wavelength is longer or shorter? Okay, so it is inversely proportional to surface temperature. So if wavelength which you detected is longer, so calculation temperature will be what? Less. Now you understand? Clear? Make sense, my dear students? Now, my dear, the distance. Distance, how it is calculated, you need to read. Standard candle is used to estimate the distance. A standard candle is something with a non-luminosity. So, will this be affected by wavelength? Tell me. The non-luminosity of any standard candle, is this affected by redshift? No. So, distance of the star in calculations will not be affected, my dear. Yes? Radius of star. Now, radius of star and Stephen and Boltzmann's law, you know, luminosity is 4 pi r square sigma T4. Make the subject radius. L over 4 pi sigma T4 square root radius. Luminosity is same. 4 pi sigma same. If observed temperature is too less, so radius calculated will be too high. Two questions are left. The sun has a surface temperature of 5780 Kelvin. Luminosity is this. Tell me, dear students, which law will be used here? And his friend's law. Luminosity, radius. Luminosity is 4 pi r square sigma T4. Radius is L over 4 pi sigma T4 square root. Put the values 3.85. All values are three significant figures. You must write the final answer also, three significant figures.
Six point nine six. 8.8.
80?
Eight.
The Earth is at a distance of 1 point this from the Sun. D. Calculate the radiant flux intensity F at the distance of this. F is equals to L over 4 pi D square. This is easy. Can you just substitute? L was how much? 3.85 10 per 26. Calculate, my dear students. 10 per how much? Watt per meter square. Wien's displacement law. The variation with the wavelength of the intensity of the sun is this. Another star has same radius, lower surface temperature. Lower surface temperature. If surface temperature is lower, so the wavelength at the peak intensity will be lower. Two things will be here, my dear, not only one actually. Why? If surface temperature is lower, so it means the luminosity 4 pi r square sigma T4. If surface temperature is lower, its luminosity is also lower, one mark. Other, Wien's displacement law says the peak wavelength is inversely proportional to surface temperature, more. So two changes you will see, my dear. One change will be the luminosity will be less. Other will be the peak wavelength will be more. So if this peak is here at this point, yani this is the peak for the sun. This is for what? Sun. So other star, how do I know that peak will be right side or left side? Lower temperature mean more wavelength. We already did a while ago similar question. So other peak might be somewhere on this line. Okay. Now, since here peak intensity is here for sun, so other will be where? I will use a red color. Below this, somewhere. Did you notice two changes will take place? The wavelength, I think you already know, because the peak temperature is surface temperature is less. So wavelength will be more. And the second, because the surface temperature is less, the luminosity will be less. So peak intensity, you will not get the same one. Two changes, my dear. Please make sure you all observe two changes. Change number one, the wavelength will be longer. Change number two, the peak will be lower. Yes or no? Alhamdulillah, correct. Redshift again. A galaxy in the constellation of Corona Borealis is moving away from Earth. Moving away means the redshifted. Yes, observed wavelength will be longer than the true wavelength. The visible spectrum from the sun is this one. The lines that are at wavelength of 397 nano, 410 nano, 434 nano, 486 nano, and 656 nano. You can see them on the top. The composition of the star, composition of sun and a star in Corona galaxy are similar. On the figure sketch, the emission of spectrum line of the star in the Corona galaxy as observed from Earth. No calculation needed. Moving away, redshifted. Redshifted means shifted towards longer wavelength. All those lines, wherever they are, shift all of them by same amount to the right side, my dear students. Yes or no? $497, 397, sir. So it will be longer now. Pattern, you should keep the same. Good. Next. Shifted. Almost same gap. Shifted. Shifted. 650. Shifted. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I shifted all of them to the red side. The concept was, if it is moving away, the observed wavelength according to Doppler's effect will be longer. So all the wavelengths I made to the right side. It's one mark. Galaxy in corona is moving away from Earth at this speed. This is called speed of recession. V, my dear students. Use the information to calculate in nano the observed wavelength of the lowest visible energy. Energy with the wavelength equation, actually, you don't know yet. It is in quantum physics, but I can help you. E is equals to HF, which means E is equals to HC over lambda. So now they are asking you energy with lowest energy. So lowest energy means what? The wavelength is longest, my dear. The wavelength is longest. Lowest energy, longest wavelength. Which was 656. Now let's read. So use this information to calculate in nanometers the observed wavelength. Which one? So you will just make that equation and solve that. So observed wavelength will be longer. So new wavelength minus original, yes? 656, right? I'm using nano so that the answer is also nano over 656 is equals to C, V over C, 21400 times 10 power 3 because of kilometer over 3.0 into 10 power 8. Dear students, you just need to rearrange this equation and solve it. You know, Doppler shift says the change in wavelength over the actual wavelength is equal to V over C. We see the only trick to this question was this number. This number. And I use the energy equation you will soon take in quantum physics. The energy of any electromagnetic radiation or photon is hc over lambda. H is Planck's constant, c is the speed of light, lambda is the wavelength. 703 nano. I use nano so that the answer is also nano. The wavelength is used to calculate the value of surface temperature of star in corona galaxy. Calculation does not give the accurate value. Which calculation? This wavelength is used to calculate the temperature. So temperature calculations are not exact. State and explain whether this value of temperature, yani the one which you calculated, is too low or too high. Yes, my dear. Easy, easy. It's just like a previous question. What can you say about the observed wavelength? More, greater, longer, too much. So according to Wien's displacement law, the surface temperature will be less. No, say decreased, less. They want to. So state and explain with the reason. So start with this wavelength, my dear. So 700, do you even know, my dear, 703 is the maximum wavelength of visible light. After that, there is nothing. Visible light is almost 400 to 700. And this is what? 703. Oh, this is the highest possible wavelength of any visible intensity. So since wavelength or peak wavelength, whatever you are saying, is too long or higher. So surface temperature is too low. You can give a reference to the Wien's displacement law, my dear, but it's actually 1 mark, so I didn't give the reference. But in case if they want to give the reference, like stating the relevant physics, then you will mention that according to Wien's displacement law. Yeah? One more question. It's the last one. What is meant by luminosity of star? Total radiant power. Total radiant power emitted by the star is called luminosity. Explain how the standard candle in a distant galaxy can be used to determine the distance of galaxy from observer. So standard candle has known luminosity. Known luminosity. Okay. Luminosity L is equals to F is equals to L over 4 pi. Yeah. So F radiant flux intensity is measured. Some people they say detected, but I'm saying measured on Earth for the same galaxy. And then use of the equation what? F is equals to L over 4 pi d square to determine the distance d. So 1 mark I just told you, the standard candle has a known luminosity. Radiant flux intensity will be measured and use the equation to find this inverse square law. The sun has a radius, this 6.96 into 10 power 8. Surface temperature, you have light observed from the sun is observed to have peak intensity as this. Calculate the luminosity of the, okay, so luminosity L is equals to 4 pi r square sigma t for 4 pi 6.96 10 power 8 square 5.67 10 power negative 8 times 5780 power 4. 3 point luminosity. What? Another star emits a radiation that has peak wavelength. This is lambda 2 max. You the second star. So this is lambda 1 max, my dear. Yes or no? Determine the surface temperature. You know that the lambda max times T is what? Constant. So lambda max 1, how much? 500, 1 nano. Surface temperature, how much? 5780. Lambda 2, how much? 624 nano. Given numbers all are three significant figures. You need to write the answer also. Three significant figures. Sorry?
4640.
You mean 4,640. Good. A last one. Last question says that figure 8.1 shows the part of the emission spectrum of a visible radiation emitted by hydrogen gas in a star in a distant galaxy. So increasing frequency is right side. The galaxy is moving away from Earth at this speed. This is speed of recession of galaxy. How the positions of the lines of the emission spectrum seen by an observer on the Earth differ from this? Of course, they will be shifted towards a lower frequency. Why did I say lower frequency? Yani shifted towards the left side. Because actually the redshift means increase wavelength. Increase wavelength means decrease in frequency. They didn't give the wavelength spectrum. They gave you frequency spectrum. So increase in wavelength mean decrease in frequency. So frequency decrease mean all these spectral lines will be moved towards the left side. Yes or no? So how these positions, how the positions of the lines in the emission spectrum seen by observer on Earth differ from the positions this. Okay. So due to recession of galaxy from Earth, yani redshift, yes? Observed frequency is less. Is less. So spectral lines will be shifted to the left, yani lower frequency. Okay. After that, my dear students, draw the three lines of spectrum positions seen by. Actually, we did last time. We did to the right side, yes, and now you will say to the left side. So 1, 2, 3. Okay. The lines in figure 8.1 correspond to the electron transition later. This is quantum physics. It's typical quantum physics. We will study later. And this we will also study later. This we can do. But the energy with the wavelength, you have the wavelength 488 nano. Speed of recession you have. So you want the wavelength in nano detected by observer on Earth. So what is the Doppler shift formula? Delta lambda over lambda is equals to V over C. Lambda minus 4, keep nano, okay? 488 over 488, 6.2 into 10 power 6, 3.0 into 10 power 8. You can type and do shift solve technology. I guess it will be more than 488.
498.
Wallah, 498 nano. Hubble's constant is this. Determine the distance of galaxy. V is equals to H naught D. And we are done. V, come. 6.2 into 10 power 6. D, Hubble's constant, 2.3.
2.7.
Something 10 power 24. Yalla.
2.7.
10 power how much?
24.